Good morning, students. How are you? I hope you are all very well. Shall I start the class? Before that, I want to tell you something. Attendance is must, so everyone should attend all the classes regularly, or else you will be losing your internal marks as well as attendance. Okay? Shall we start the class? In this semester, you are having 5 major papers. One of them is complex analysis. I am going to teach you complex analysis. Okay. I think you are familiar with all the properties of real number system. Now, let us assume an equation x square plus a is equal to 0. Now, we discuss about the introduction of complex number. Consider an equation x square plus a is equal to 0. Let us find the solution of this equation as x square is equal to minus a. Does this equation has a solution in real number system? Of course not, because any square of any real number cannot be negative. In order to find the solution of the equation like this, we have introduced a new number system, that is called it as a complex number system. In this chapter, we develop basic algebraic and geometric properties of complex number system. Now, let us see the definition of complex number. I guess everyone knows the general form of complex number. Now, the definition of complex number. A complex number is of the form x plus iy, where x and y are real numbers. X and y are real numbers, and this I is an imaginary unit. I is an imaginary unit with the property I square is equal to minus 1. This complex number z is equal to x plus iy. This x is called the real part and y is called the imaginary part. And we write x is equal to real z and y is equal to imaginary z. If x is equal to 0, then the complex number z is purely imaginary. If y is equal to 0, then z is real. Now, the two complex numbers are said to be equal if and only if they have the same real and imaginary parts. Now, let us define the addition and the set of all complex number is denoted by capital C and is defined to be the set of all z is equal to x plus iy, such that x and y belongs to R. This is a set of all complex number. Okay. Next, we define addition and multiplication of complex numbers. We know that the fundamental operations are used in R, likewise also applicable in C. Now, let us take two complex numbers. Let z1 is equal to x1 plus I y1 and z2 is equal to x2 plus I y2. Then, the addition of two complex numbers z1 plus z2 is equal to x1 plus x2 plus I into y1 plus y2. And multiplication of two complex numbers z1 z2 is equal to x1 x2 minus y1 y2 plus I into x1 y2 plus x2 y1. This is addition and multiplication of two complex numbers. Next, we see the theorem. Next, let us see the theorem. The statement of the theorem is The set of all complex numbers C is a field under addition and multiplication. Under addition and multiplication. You know that the addition of two complex number and how to define the addition of two complex number and multiplication of complex numbers. Okay, what does it mean by, what does this means? C is a field. What does it mean by field? Field is nothing but a system. For example, a system F plus dot is a field if it's satisfying the following conditions. They are F comma plus is an abelian group. The second one is non-zero F dot is an abelian group. The third one is distributive law. Distributive laws are hold for all A comma B comma C belongs to F. What is field? Field is nothing but a system satisfying these conditions. Okay, what do we have to prove this theorem? Now let us see the proof of the theorem. What do we have to prove? First we have to prove C comma plus is an abelian group. What does it mean by abelian group? What does it mean by abelian group? Group with commutative property. We say that an abelian group. Group is nothing but again a system satisfying some conditions. Okay, the condition is closure property. Addition is closed. Second one, addition is associative, and existence of additive identity and existence of additive inverse with commutative property. Then we will prove the C comma plus is an abelian group. Okay. Obviously, Z1 plus Z2 and Z1 into Z2 belongs to C. Since the addition of real number is associative and commutative, it follows that in addition, the addition in C is also associative and commutative. I repeat once again, since the addition of real number is associative and commutative, it follows that in addition in C is also associative and commutative. Okay. Now, next to find the additive identity. The additive identity is in C, satisfying C. The additive identity is nothing but 0 is equal to, what is additive identity? 0 is an additive identity. So 0 is equal to 0 plus I0 is the additive identity of, is an additive identity of Z is equal to x plus iy. And then we have to prove the additive inverse of a complex number. Z is equal to x plus iy. The additive inverse of Z is equal to x plus the additive inverse of Z is equal to x plus iy is, finally we find the additive inverse of a complex number. Z is equal to x plus iy. Then the additive inverse of Z is equal to x plus iy is Z is equal to minus x plus I into minus y. Okay. These things, closure property, associative, existence of identity, existence of inverse, and also commutative property, we get C comma plus is an abelian group. C comma plus is an abelian group. Next, we have have to prove non-zero C dot is an abelian group. Non-zero C dot is an abelian group. Now, let us take two non-zero complex numbers. Z1, Z2 belongs to C star. What does mean by C star? C star means the set of all non-zero complex numbers. The set of all non-zero complex numbers. Then Z1 is equal to x1 plus I y1 and Z2 is equal to x2 plus I y2. Where x1 and y1 are not simultaneously 0 or not simultaneously 0. And also x2 and y2 are not simultaneously 0 or not simultaneously 0. What does this means? If Z1 and Z2 are non-zero, then x1 and x2 are not simultaneously equal to 0. If either x1 is equal to 0 or y1 is equal to 0. Z2 is non-zero means x2 and y2 are not simultaneously 0. That means either x2 0 or y2 0.